know. So any doubt related to the till week 4? If you have
No,
any
sir.
doubt, you can ask. Are you saying something?
Sir, no doubt up to week 4, sir. Week 5.
Any doubt related to the lab part?
Yes, sir. How to submit the lab? Where to submit?
Hmm?
So how to submit the lab where we have to do the experiment in early spices or
Okay. Yeah. For the lab part, what is the thing is that I have given you one circuit, experiment one. Okay, there is one circuit. If you see, you have to create that circuit on a LT spice. Okay. Now the thing is that if you are implementing this circuit on a LT spice, there are two components. I think one is the MCP6004. One is this component, and second component is, just wait a minute.
LM39.
Yeah, LM339. Okay, LM339. These two components are not available. So what you have to do, you have to create this component. Okay. So in that particularly part, what you require two things. One is the symbol, and one is their LT spice model. Spice model basically, not LT. We are saying the spice model. Similarly, for that LM339, you require again two things. One is the symbol, and one is the spice model. With the help of these two things, yeah. Now the symbol is that you know that this is the LM339 is basically a comparator. Okay, operation amplifier. So the symbol of that one is the operation amp symbol of this one, and MCP64404. The symbol of that one is also same, but only the spice model is different. Okay, so you have to search out the spice model of that one. You can easily search out that particularly on the net. Okay, just search out MCP6004 spice model. Okay, so where all the particularly details will be available with that. Okay, so with the help of this one, you can create. Is it clear? So you have to create these two symbols. Now you can use this symbol for the circuit design. Symbol with the LT spice, you can create these two symbols. Now after creating these symbols, you have to create your circuit that is given in the experiment one. Now the point is that you have to find out the resistors. Okay. If you see that there are some particularly things is given. One is the supply voltage. VDD is given that 5 volt. Okay, and particularly input supply voltage is 1 to 1. Input supply voltage is 1 volt. The frequency of this one is 5 kilohertz. One thing you have to change is that the frequency of this one. I will reshare that particularly because 100 kilohertz frequency is not possible. So you have to change it as a 5 kilohertz. Okay. Now Vm, the equation one is given. Vm is equal to 2 R2 by R3 into VCM. VCM is what? It is given that it is VDD by 2. VDD is what? 5 volt. So VCM is 2.5 volt. So VCM we are using the 2.5 volt. On the basis of this one, you set the value of R2 and R3 and your Vm value will be calculated. Okay. So okay, now if you go with this circuit part, so you can see that R1 and C1. C1 is used as a feedback and R1 is as a input signal. And VCM is applied as the positive terminal. So on the basis of this one, can you calculate the equation of that particularly ramp signal? Okay. Now calculate this ramp signal equation and just compare this ramp signal equation with the equation number 1. So you will get the components values. Okay. Similarly, the frequency, this particularly is used for the low pass filter or basically the high pass filter or low pass filter. So according to that one, you can calculate the frequency part also. So in the week 5, this is a basically simple a filter or basically we can say the integrator or differentiator circuit. Okay, so in the week 5, you will discuss that one integrator, differentiator and the filters part. So with the help of this integrator and differentiator, you know the equation of ramp signal. Compare this ramp signal equation with the equation number 1, you get all the components value. That is a theoretical calculation. Now use this particularly values of R1, R, C1, R2, R3 in a way that you are getting the appropriate value. Now you can use this resistor value in a LT spice. Okay, use this resistor value in a LT spice and finally check that you are getting the correct output or not in LT spice. Okay. Any doubt? So with the help of equations, with the help of equations, you will calculate the value of R1, C1, R2, and R3. Okay. Now use this particularly R1, C1, R2, R3 in LT spice and observe the voltage. Observe the. Okay, this is your first task. Second task is that you have to use this R1, C1, R2, R3 on a breadboard. You have to prepare the circuit on a breadboard. Prepare a circuit on breadboard. Provide the supply 5 volt and 5 kilohertz using ADML kit. Okay, and observe the waveform. Okay, this is your second task. So these two tasks you have to perform. One is what? Calculate the R, C, R1, R2, R3 values. Use that value in LT spice and observe the voltage waveform to the LT spice. In the LT spice. And second, on prepare that circuit, make that circuit on a breadboard, provide the supply and frequency using the ADML kit and observe the waveform. These two tasks you have to perform. Now the thing is that submission part. Now in the submission part, what you have to do, you have to prepare on a drive. In your study drive, you have to create a folder by the name of experiment 1. Okay. Give the right that anyone with the link can access this folder. Now in this folder you have to prepare, you have to put three things. One is your LT spice file. Okay. One is your video, that is basically the explanation of circuit. Okay, and third one is the report. In this your LT spice circuit, your waveform calculation, okay, how you calculate the R1, C1, R2 and R3. So this calculation, Okay, all the things will be in that report. Okay. Any doubt? Just any doubt?
No, sir.
If any doubt, you can ask the questions. Just wait for a minute. Yes. If you have any doubt, you can ask about the lab part. Is it clear? Okay. So now we start the week 5 content. Have you gone through with the week 5 content?
Yes, sir.
Okay. So any doubt you are facing in that part? Week 5?
Sir, can you revise week 5 also?
Okay. So just wait a minute. Yes. So basically in the week 5 we start with the filters. Okay, so for that one we basically switch to the frequency domain. Now first thing is that why the filter is required. The basic requirement of the filter is to select particular frequency. Okay. If we want to select a low, if we want to pass a low frequency, we require a low pass filter. If we want to pass a high frequency, we require a high pass filter. Or sometimes we require some desirable frequency, so we can use the desired frequency. So we use the band pass filter. And sometimes we require to stop desired frequency, we use the band stop filter. So basically four types of filter generally we consider. Along with that one is the all pass filter. All pass filter. Now the requirement is why. What is the requirement? In the communication part, when we transmit some signals, you know that in the environment all different frequencies are available. We have a Bluetooth frequency, we have a RF signal frequency, we have a 2G spectrum, 3G spectrum, 4G spectrum, 5G spectrum. So all the frequencies we have. Okay. Now the thing is that when we transmit our signal, along with that we have the AM signal frequency, we have the FM signal frequencies. Okay. Some particularly satellite communication frequencies. Okay, so all the frequencies we have. Now the thing is that we require only a particular frequency. Then what we have to do? We have to pass through a system that will pass desired frequency and stop remaining frequency. Okay, that will pass the desired frequency and stop the remaining frequency. So for that one, that system is called the filter. That system is called the filter. Okay. Now the generally response of the ideal low pass filter is that they have this response. Okay. So below the frequency of omega c cutoff frequency, that will be pass all the frequency with a system response of 1. Okay, and after the cutoff frequency they will stop all the frequency or multiply with the 0, so all the frequency will be stopped. Okay, so that is the low pass filter, but that is ideally low pass filter. If we draw the symbol of that low pass filter is two particularly low pass filter will be pass, so low frequencies will be pass. So that is the symbol of low pass filter. But practically, it is not possible. So practically, the filter response should be like this. Okay, it is 1. From here, it will be start decreasing. It is called the cutoff frequency, where the magnitude will be dropped by the maximum magnitude multiplied by the 1 by 2 times, 1 by root 2 times. Okay, or we can say it is a 3 dB point. It is a 3 dB point. Why? Because the maximum magnitude is 1. If the magnitude is reduced by the 1 upon root 2 times, so basically 1 upon root 2 is called 0.707. Okay, and if you convert into a dB, so its value is the 3 dB. Its value is 3 dB. Okay, so where the magnitude will be reduced either the 3 dB or the 1 upon root 2 time of the maximum magnitude, that is called the 3 dB point. And we calculate the frequency with respect to this 3 dB point. So that frequency is called the omega. Now this transition, so this transition will be depend on the filter. When you go with the control system, you can see that this particularly transition from the high pass band to the stop band. Okay, this transition will be defined with the order filter. If we are saying that our filter is first order, the slope is minus 20 dB per decade. What is the meaning of that one is with 10 times variation in frequency, slope will be reduced minus 20 dB. Okay, if you are talking about the second order filter, the slope is minus 40 dB per decade. So that means slope is little bit faster. Okay, if we go with the third order, the slope is minus 60 dB per decade. The slope is little bit more faster. Okay, so if we increase the order of the filters, so we can get this particular transition. But the thing is that when we increase order of filter, my filter stability will be reduced. Well, so that's why we just only go with the first order, second order, or maximum in the third order. Okay, maximum in the third order filter, not more than that one. But that particular third order is also sometimes it is unstable. That is dependent on the gain. Okay, that is dependent on the gain. So that's why we can say that this ideal response is this particularly response with zero transition is a ideal. This is the ideal. That is not possible practically. Okay, and this is the practical low pass. Clear? Now the band that particularly the frequency that is passed through the low pass filter, it is called the pass band, and the frequency that is stopped through the low pass filter, that is called the stop. Okay, so this is pass band, and from that to the higher frequency it is called the stop. Clear? Any doubt? Now similarly for the high pass filter, ideal responses, lower frequency will be stop and higher frequency will be the pass. And practically responses, this is the gain, frequency, frequency, that is the omega c, that is the 3 dB point, that is called the omega c. What is 3 dB point? Again, the maximum magnitude is 1, so the 1 upon root 2 time of the maximum. 1.1 upon root 2 time of the maximum, or the basically 70.7% or 0.707% of the maximum. Okay, this one is called the stop band. That pass band. Stop band. After that, pass band. Okay. The particularly symbol of that high pass filter is these two will be pass, so it is a high pass. Upper two is pass, so this is the low pass. Bottom two will be pass, it is a high pass. Third is the band. Frequency, ideal band pass filter, practical pass filter, gain one. Okay. Again, the point 3 dB point is that where the magnitude is 1 upon root 2 times of the maximum. Okay, if this is the maximum point, so 1 upon root 2 times of the maximum. Okay. With respect to this one, we are getting two frequencies. One is the omega 1 and one is the omega 2. Here it is the omega 1. Omega 1 or omega C1, we can say omega C1 and omega C2. omega C1, omega C. Okay, between these two frequency, it is called a pass band. And this one and this one is stop band. Similarly, pass band, stop band, and stop. Okay, any doubt? Yes, any doubt? If you are talking about a single circuit. Okay, and band stop filter is just opposite to that. Now the thing is that in the high pass filter or band low pass filter, we required one cutoff frequency. Okay, omega C, omega C, omega C. So that means we required only one R and C combination. Okay, the arrangement is anyway like resistor in series and the capacitor is in parallel, or basically capacitor in series, resistor in parallel. That will be decided by the low pass or high pass filter. But the thing is that we only generate one frequency. So for one frequency will be generated by a single RC component. Okay, single RC component, because you are already discussed about the RC filter. So RC filter frequency F is equal to 1 upon 2 pi root RC. Okay, I think you have already studied about this one in your ESTC or EEC, I think so. Okay, whereas in the case of band pass filter or band stop filter, you require two different frequencies. That means you require two RC combination. Okay, with the help of R1 C1, you will get the F1. F1 is equal to 1 upon 2 pi R1 C1. And similarly, you again require one or other component, that is the R2 and C2. C2 R2. So with respect to this one, you are getting F2, that is nothing but 1 upon 2 pi R2 C2. Okay, so that means you require two resistance capacitor pair combination. Okay, now if in a circuit, if two storage element, basically storing devices are used, either that is a voltage storing device or the current storing device, either the inductor or capacitor, so that filter is called the second order filter. So remember that two things is low pass filter and high pass filter is a first order filter. We can create a second order and third order also, low pass and high pass. That is not a essential that only the first order filter, but the minimum condition is that you can require only a first order filter. This is the minimum condition. Either you can go to the second order, you can go to the third order also for the basically slope reductions. Okay. Whereas for the band pass filter and band stop filter, the minimum condition is that is second order system. Okay, is it clear? Now the first order response will be calculated, defined as a h of j omega is equal to 1 plus 1 upon 1 plus s upon omega. H of s, or basically s, h of, I just put as h of s. Okay, where h omega p is the pole frequencies. Pole frequency. Basically, pole frequency is what? Where the transition is start. Transition is started. I think you study about the body plot. Okay. So in the case of body plot, if you remember, like this is my diagram. So if one pole will be exist, after that it will be started 20 dB, minus 20 dB per decade. If second pole is exists, so minus 20 already and minus 20 again. So minus 40 dB flow. Okay. So that's why it is called the pole frequency, or basically the frequency of the transition. And omega, this particularly S is frequency variable frequency. Variable frequency. Okay, so H of S is j omega, so I just put it as a 1 plus j omega upon omega p. Okay, if I take the magnitude of this one, so H of j omega magnitude is 1 upon root 1 plus omega upon omega p square. Real component is square plus imaginary component is square and square root of this one. So this is the way to calculate the magnitude. Now, if omega is equal to omega, okay, if omega is equal to omega p, so h j omega p is what? 1 upon root 1 plus this omega is equal to omega p, so basically both will be cancelled out. 1 is 1 of is square of 1 is again 1, so 1 plus 1 is 2. So that is 1 upon. So generally we can say when the omega is equal to omega p, your magnitude h of j omega is equal to 1 upon root 2 times. Okay, so if my omega p is this one, if I say this is my omega p, so when the frequency omega is equal to omega p, there the magnitude is 1 upon root 2. Okay, if I calculate the angle of that one, so what is the angle? Angle of h of j omega is equal to minus tan inverse omega upon omega p divided by 1. Okay, how we calculate the magnet angle? The angle of numerator minus angle of denominator. And the angle of numerator is how we calculate tan inverse imaginary component upon real component. Okay, so imaginary component is 0, so that means tan inverse 0. Tan inverse 0 is 0. So that's why I am not including the numerator angle. Directly I calculate the denominator angle, and what is the denominator angle is tan inverse omega upon omega p divided by 1, because imaginary component is what? Omega upon omega p. So tan inverse omega upon omega p divided by 1. So this is my angle. Okay. Now if omega is equal to omega p, so that means angle of h j omega is what? Minus tan inverse 1. And that is nothing but 45 degrees with minus sign. Okay. So if you check at this point, if you take a slope at this point, okay, this is my slope. The slope is minus 45 degrees. Okay. Any doubt? Now if we are going to implement that one, so we have a one R, we have one C. Okay, this is grounded. Input signal Vi. This is the output signal V naught. So can you calculate the transfer function? So V naught upon Va. What is V naught? This is the R 1 by Cs. Okay, the volt current across this particularly 1 by Cs. That is the V naught. So V naught is what? 1 by Cs time I of S. Okay, and this voltage, input voltage will be drop across this resistor and this capacitor. So Vi is nothing but Ri plus 1 by Cs time I of S. Ri of S. Okay, so if I put this V naught and Vi value, so 1 upon Cs I of S is upon I of S, I take it common, so it is R plus 1 by Cs. Or we can say that 1 upon 1 plus RCS. Okay. Now, if V naught upon Vi is equal to 1 upon 1 plus S upon 1 by RC. So 1 by RC is what? Omega P. Okay. 1 by RC is what? Omega P. So if I put 1 by RC as a omega P, so it is a generalized equation V naught upon Vi is equal to 1 upon 1 plus S upon omega. Okay. So if omega P is equal to 1 by RC, so what is the FP? FP is what? 2 pi. FP is omega P. So FP is nothing but 1 upon 2 pi RC. Clear? Now, now the thing is that if I design a filter, mm, that is my filter. Okay. Now that filter will be apply on a RL load. Okay. I assume that this particularly load is a resistive load. So finally we are getting the output. Okay. Finally we are getting the output. So basically what happens is that we have to connect the filter response with any of the load, and that load I just assume that it is a RL. So what is the effect of this RL is, so my circuit should be, this is the R 1 upon CS and RL. This is the final output we are getting. Now the thing is that my VO is changed, my VI is changed. So what is VO? VO is nothing but is a parallel combination of these two RL and 1 by CS and the current flowing through this particularly. So current is, I just say that it is IS multiplied by the parallel combination of R and 1 by CS. So how we calculate the parallel combination? RL into 1 by CS upon RL plus 1 by CS. Okay, so this is the V naught. Now what is VI? VI is also the voltage of across this resistor and parallel combination of these two. So that is the R plus parallel combination. So RL multiplied by 1 by CS upon RL plus 1 by CS. This whole resistance multiplied by the IS. So what is the V naught is RL upon 1 plus RLCS time IS. And VI is R plus RL upon 1 plus RLCS time IS. So V naught upon VI is what? RL upon 1 plus RLCS plus RL. Denominator both will be cancelled out and the current IS is also cancelled out. Now if you go with the previous circuit, so in the previous case, what is the transfer function? V naught upon VI is 1 upon 1 plus RCS. Okay, now in this one, so we have to take, initially we have to equate the numerator part as a 1. So what should I do? I just divide with the RL. So V naught upon VI is, if I divide this numerator and denominator with the RL, so it is a 1 divided by RL divided by RL is 1 plus this RL and divided, this particular term will be divided by RL, so RL and RL cancel out, so that is the 1 plus RCS plus 1 by R. Okay, so this term is same, only the 1 plus RL term will be included. Okay, or we can basically take this way as a Sorry, this is the R plus R upon RL term will be yeah, R plus RL R6. Yeah, R this term will be added. Okay, and if we do the numerator as it is, I just take a R plus RL as a common. So B naught upon BI. Just take the R plus RL from the denominator will be common and take it as a outside. RL upon R plus RL divided by R plus RL. I already taken common, so 1 plus RL upon R plus RL CS. Okay. Now the DC gain without the load, DC gain is nothing but the numerator. This is the DC gain and that is 1. And with load, the DC gain is RL upon R plus RL, that is less than 1. Okay, so because of adding the load resistance, we are saying my DC gain is reduced. Second, the frequency is what? Omega P is nothing but 1 upon RC. Okay, I just put that equation as a 1 upon 1 plus S upon 1 by RC. Here if I put it as a, so it is a RL upon R plus RL divided by 1 plus S divided by 1 by C time RL upon R plus R. Okay, so the frequency is what? 1 by C into RL upon R plus RL. Or I can say that 1 upon C into R parallel combination with. Okay. Now the frequency is also less than 1 upon RC. Okay, also less than 1 upon RC. So what is the effect if we are adding the load resistance? So first is the DC gain reduce. And second thing is that frequency of operation is also reduced. Okay. So the gain as well as the frequency of operation will be vary. Another thing is that my load is not a constant. Okay. Sometime I use one load, sometime I use another load. Like for example, I am using connecting this filter with the mobile phone. Okay. So the other component, mobile phone component, having the different resistance. Similar thing, I use that filter for my RF module or basically with my tab or basically with my laptop. So the resistance will be different. So if resistance will vary, the frequency of operation is vary. The same filter that we are using, okay, the same filter that we are using, if the resistance will be changed, the frequency of operation will be changed. One particularly filter will pass a 1 megahertz frequency. The same filter with other device will be passed 2 megahertz frequency. Why? Because the omega p will be changed. The same filter without any changing the R and C value will pass a 3 megahertz. Okay, so every time the frequency of operation is vary. Why? Because your load resistance is vary. Clear? Any doubt? Now the thing is that when we design a filter, we have to finalize that that particularly filter response or filter characteristics not dependent on the resistance value or a load resistance value, because the load is not a constant. The load will be vary. Okay, the load will be variable. So basically, to reduce the effect of this load resistance RL, what should I do? I just use a stray capacitor. So I am using a stray capacitor. I am using a stray capacitor. Okay, so I am using in a parallel with this capacitor. I am using the stray capacitor. So because of this stray capacitor, now my frequency, the particularly capacitor value will be the two parallel capacitors. So my circuit should be like one resistor with one capacitor, another capacitor. That is the RC, CPN. Okay. So basically, the value changes with respect to R now will be compensated with respect to the CP, because we know when these two capacitors are connected in a parallel. Okay, these two capacitors are connected in a parallel. So basically, overall C equivalent is what? C plus CP. Okay, so the frequency that will be reduced because of this R parallel with RC. Now we have the frequency C into R parallel with RL, that is less than 1 by RC. Why? Because this combination always a less than with R. Okay, so if this one is R, sorry, this frequency is greater than, not less than. The frequency of operation is greater than. Okay, because this one is less than R. So if it is a less than R, so basically 1 upon C multiplied by the R parallel with RL should be higher than 1 by RC. Now what should I do? I just use a increase the value of capacitor C plus CP in a way that means the multiplication of this one is almost equal to the R. How much R will be reduced? That will be compensated by increasing the value of C. So the multiplication of these two will be a constant. Okay. So my filter is Vi RC. Okay. So this is my filter, low pass filter. How this is a low pass filter? We can calculate the transfer function. So what is the transfer function V naught upon Vi? This is the 0. Why? Because of the virtual ground concept. So Vi by R Vi minus 0 by R, the current that is going in this direction will be passing through this one, equal to 0 minus V naught by 1 by Cs. So V naught upon Vi is I can calculate the V naught. So V naught is what? Minus 1 by RC S time Vi. Basically, in the Laplace, you just see that 1 by RC and 1 upon S is basically the integrator. So Vi. Okay. So V naught is nothing but minus 1 by RC integration of VID. So that is a integrator. Any doubt?
No, sir.
Okay. Now if we are getting the transfer function of that one, mm, yes. Now the thing is that when you are using the AC signal, the capacitor impedance is Z is equal to 1 upon J omega C. Okay. And if omega will be exist, so that is not equal to 0 or that is also not equal to the infinite. But for the DC signal, we know that capacitor is behave as a open circuit. Why? Because frequency omega is 0. So if omega is 0, so 1 upon 0 is infinite. So that says infinite. So that particularly the problem is the with the DC signal is that in DC signal, if my VI input is the DC signal, then this capacitor is not useful for the feedback. So what should we do? We require one additional circuit for that. Okay, we require one additional resistor for this one feedback part. So that means if that particularly circuit will be applicable either for the AC signal as well as for the DC component. Okay, or you can check with that circuit also. You can calculate with this circuit also. This is the VI. So the 1 by C, V naught. Okay, now if we say that this point voltage is the Vx, okay, the current is I is flowing, so I multiply by R is nothing but Vi minus Vx. Okay, and we know that Vx is nothing but the V naught. So IR is Vi minus V naught. Okay, and Vi is V naught is 1 by RC integration of VIT dt with minus sign. So we say that Vx is the voltage of across the resistor. So Vx is nothing but Vi plus. Why plus? Because this minus and this minus become plus. So 1 by RC integration of VIT. Okay. Now what will be going on with this particularly is my Vx is nothing but this voltage plus this voltage. Okay, so if I draw a operation amplifier, this one, this is the minus, this is the plus, resistor, and this capacitor. This is the V naught, ground, this is the Vi. Okay, now we are getting this one, but we required one more voltage, that is the Vi. We required one more Vi. So what should we do? We are connecting this one as a minus V naught by R. Okay, and this is a V naught minus V naught, and this is a V naught. So what should we do? We connect this one from here. because we are getting the V naught as a negative. So that is also the minus V naught. So we are getting this circuit, and the simplified version of that one is this is the minus R Vi along with the capacitor, and in the parallel it is a resistor. That is the V naught. With the plus sign, it is a grounded. Vi, that is the R, that is C. Okay. So the circuit, that circuit is just equivalent to this circuit. Both will be equal. Now, if this circuit will be given me the V naught upon Vi is equal to 1 upon 1 plus RCS. So that means this circuit also give me the V naught upon Vi is equal to 1 upon 1 plus RCS. Okay, we can check this one also. How we can check? Again, the incoming current will be the outgoing current and outgoing current. So I will say this is the I1, I2, I3. So we can say I1 is equal to I2 plus I. What is I1? Vi minus 0 by R, because this point voltage is the 0 voltage because of virtual ground, is equal to 0 minus V naught by R, that is I3, plus 0 minus V naught by 1 by Cs, that is I2. So Vi by R is equal to minus V naught, I am taking common, that is a 1 by R plus 1 upon 1 by Cs, that is Cs. Okay, so Vi by R is equal to minus V naught, that is 1 plus RCS upon R. So both will be cancelled out. So V naught upon Vi is nothing but minus 1 upon 1 plus RCS. Okay. Now the thing is that here we are getting the directly 1 upon 1 plus RCS. Here we are getting a minus 1 upon 1 plus RCS. So this minus sign is why? Because we are using the inverting amplifier. Okay, but if we are talking about the gain, so V naught upon Vi more, that is equal to nothing but 1 upon 1 plus RCS. If you are talking about only the magnitude, so the magnitude will same, but minus sign is because of the inverting amplifier. There is a phase shift of 180 that will be given by the operation. Okay, to overcome this phase shift, what we do? We are just required one more operation amplifier here. With a negative sign, positive sign, grounded. This is the resistor. Again, the feedback, we are using the value R and R. So here we are getting the this particularly minus. Okay. Now what is the gain of this one? Minus R by R into, if I say this is the Vx. Vx is equal to V naught. Okay. So nothing but it is a minus Vx is equal to V naught. Now this is Vx. If I say this is the Vx. So minus it only the in for the inversion purpose. Okay, unity gain inverting amplifier. So that will be only provide the 180 degree phase shift. Okay, so this minus sign will be eliminated by this operation. Okay, so this is your low pass filter. Any doubt? Yes, any doubt? Okay, so I think no doubt till here. Now, if you check, this is my feedback circuit. So this is my feedback. Okay, so what is the feedback? The feedback is R into 1 by Cs, because this is a parallel combination, upon R plus 1 by Cs. So it is R upon 1 plus R Cs. Okay. Now, I think after that we discuss. Now, yeah, one more thing with that is, if I use the RL after that, okay, so you can see this is my V naught. Okay, so what is the V naught we are getting? V naught is nothing but minus Vi 1 upon 1 plus RCS. Okay, so this V out voltage is dependent on Vi 1 plus RCS. So that means this resistor, and this resistor, this capacitor. Okay, so all three components dependent on all these three components. There is V naught is not dependent on, so V naught is not dependent on, or not a function of RL. Okay, so the benefit of that one is that if you change the load, RL, the frequency remains constant. Okay, frequency remains constant. So this is the benefit of using the operation amplifier for the first order filter. If you can create your first order filter with the help of RC combination circuit also, okay, you can create your first order filter with RC circuit without using operation amplifier. But the thing is that RL, if RL change, gain change, frequency change. Okay, now you can create the same circuit with the operational amplifier also, but in the operational amplifier the output voltage doesn't depend on the RL. If you change the RL, there is no change in the frequency, no change in the gain. That will remain a constant. Okay. Then first total high pass filter. The response of high pass filter H of S is S upon omega P divided by 1 upon S plus omega. Or sometimes it is written as a 1 upon 1 plus omega P by S. Okay. You can check with this particular transfer function also, because if you put as S is equal to j omega, so H of j omega is nothing but j omega upon omega P upon 1 plus j omega upon omega P, or that is also equal to 1 upon 1 plus omega P by j omega. Now, how you check that it is a low pass high pass filter response? So just put as omega is equal to 0. Okay, so what will happen? In this one, you are getting 0 divided by 1 plus 0. Okay, or in this one you are what you are getting 1 upon 1 plus infinite. So 1 upon 1 plus infinite is infinite. So 1 upon infinite is 0. So at omega is equal to 0, the output is 0. Okay, so that means for the low frequency it will not pass. If omega is equal to infinite, so h of j omega is infinite upon 1 plus infinite. So infinite upon infinite. Okay, that is undefined. So you have to use the L hospital rule. Okay, if we go to the with this one, so that is 1 upon 1 plus omega p upon infinite. So that is 0. Okay, that is 0. So that is 1 upon 1 plus 0 becomes 1. So for the high frequency, the gain is 1. For the low frequency, gain is 0. The response is high pass. Okay, the response is high pass. Now, if you design the high pass filter with the RC circuit, so your circuit should be R and C. You are getting the V naught upon VI is nothing but S R C upon 1 plus S R C. Okay, so you convert it S upon 1 by RC upon 1 plus S by 1 upon RC. And 1 upon RC is what? Omega P. So you have a S upon omega P upon 1 plus S upon. Okay. If you design the same circuit with the operation amplifier, only the thing is that you have to change it with the capacitor. Okay, there is not a big deal that you can use the R in the downward and C is the upward. Okay, you can interchange that one also, no issue with that. Now if you are getting the transfer function, so that voltage is 0, the incoming current is I1, outgoing current is I2 and I3. So Vi minus 0 divided by 1 by Cs is equal to 0 minus V0 divided by 1 by Cs plus 0 minus V0 divided by R. So Vi upon 1 by Cs is equal to minus V0 1 by R plus 1 by Cs. So that is equal to minus V0 RCS plus 1 upon R. Okay, and if I take the Vi, so V0 upon Vi is nothing but R upon 1 plus RCS divided by 1 upon C. So that is nothing but RCS upon 1 plus RCS. Same response as high pass.
Sir, negative sign.
How? Yeah, negative sign. Sorry. Okay. Again, we can remove the negative sign again using the inverting amplifier with the unity gain. Okay, so you can remove that one, or you can take a magnitude of that one. So V0 upon Vi, magnitude of that one is RCS upon 1 plus. Okay, so that is the similar to the high pass. Clear? Just any doubt? Clear? So I think we will stop here with the first order, and the next, I think class is on Friday, so we will discuss the second order filter and the problems with that. Okay. Now, if you have any doubt, you can ask. If you have any doubt, you can ask.
No, sir.
Okay, so thank you all.